Today we will be discussing counters, specifically how to truncate counters. So on the screen we begin with a typical or a simple counter that is counting forward. You can see it's counting forward because it's triggered on the falling edge, and we also know that it's counting because the flip-flops are doing nothing more than just dividing the frequency in half. So a counter is nothing more than a frequency divider that divides the frequency of each bit by 2 every time. Again, just a quick recap: to make it count forward, you trigger on the falling edge. The only thing you would have to change to count it counting in reverse is you would have to change the clock connection to the not Q to trigger on the rising edge. Okay, so starting with the counter, how do we make them stop and start at a different number? So just to make sure we know that the numbers are in the right order, these I have them just coming out of the flip-flop so you can tell they're not in order. So what I'm going to do is I'm going to put them in the right order by putting the bits with the least significant bit being the ones place all the way to the right, and I'll change the labels so you can see how they should match up. Oh, it's a little bit off, but that's okay. Let's see if we can get them organized. There it is. And then the last place to the left is the 8th place. These numbers can be any order really, but we try to keep them in order so that we know that the ones place is the least significant bit or all the way to the right. If you're having a little bit of troubles following the counting sequence, you can also place a hex display, which exists only in multisim. So you go to place component and you go to indicators, hex display, and it's called DCD hex, which is a hexadecimal binary or binary to hexadecimal converter. So I'll put this over here on the right hand side. The way that it's going to work is the ones place is all the way on the right, and you connect it to the ones place, and so on and so forth. So what we'll have here is when I start my simulation, my counter will be counting forward and the hex display will be translating into hexadecimal, meaning that after 9 you'll see how it shows A, etc., B, E, C. And when it reaches F or 15, it counts again starting from the starting sequence, which is 0. So how do we make it count from another number to another number instead of using the entire sequence? So the first thing I want you to think about is, okay, let's say I want to turn this is a little green probe. I want to turn on this green probe when my counting sequence it's, let's say, 5. So whenever the counting is exactly here we go, I want this little green light to turn on. So most students will say, well, just put an AND gate, TTL 74LS08, which is a 2-input AND gate, and check that the 4 and the 1 are on. And that's partially correct. I connected to the 4's place and to the 1's place, and this light will turn on whenever it's a 5. However, the light will also turn on when it's anything else that has a 4 and a 1. For example, at 5, it also turns on at 7. It will also turn on when it's a 4 and a 1 with an 8, which will be a 13 right here. So the modification that we need to make so that this light only turns on with a 5, a 4 and a 1, we don't only have to check that it's a 4 and a 1, we also have to check that it's not a 2 and not an 8. So instead of using a 4-input AND, I could have just replaced it. Let's see, to show you in case you don't know how to replace components, you right click and you go to replace components. And I'm going to replace it with a 4-input AND gate, which is 74LS21. And the difference between N and D is just the pinout. When you buy them physically, the legs are different for soldering or breadboarding. So that's my 4-input AND. So what I have to do is I have to check that it is a 1 and a 8. However, it is not a 1 and a 4, but not an 8 and not a 2. I'm just spacing it so that I can place the components in there. So now I need to put inverters on the ones that I want them to be off. TTL 74LS04N. So I'm going to place one. I'm not going to breadboard this, so I'm not going to really worry about the pin numbers, so I can copy and paste. So in order for it to check that it's a 5, I copied and paste. Oh, that's not gonna fit there. There's like a little space that you have to have for each component, and that one was violating its space. There it is. Okay, so at this moment, by putting an inverter here and here, the 8 is going to be a 0, which is going to translate to a 1 for the AND gate. The 2 is going to be a 0, which is going to translate to a 1 for the AND gate. And the 2 should be 1. So the only time this little green light is going to turn on is whenever is exactly 5 in binary and nothing else, even though the 4 and the 1 bits can be on. See, it turns on there. However, it does not turn on there, or when it's 13. Okay, so that's the first step. We're going to keep scaffolding until we get a counter that has other limits other than 8 and 15. So instead of just turning on this little green light when it reaches 5, what I would like you to consider is the following. Not only turn on this little green light, but also the moment it counts to 5, immediately come back and start back at 0. So force all of these flip-flops to 0. So take a moment to think about it. What do I need to do to any of these flip-flops to override, to force a 0? If your answer was activate the clear, you're correct. So what I'm going to do is, first I have to stop my simulation so I can edit. I'm going to delete all of those, and I'm going to connect the output of the AND gate to all of these clears. Now, this is almost right. It's not going to work, but let me show you why. So here, what's happening is that this is not giving us a 5. The AND is giving us a 0. The thing is, the clears are active low, meaning they need a 0 to activate. So they're all being cleared at the moment. At this point, we got to realize that because these activate with a 0, we want the AND gate to give it a 0 when we want to clear it. Therefore, we need to put an inverter here on the signal. So you have two choices. You can put an inverter, like I'm about to do, and then when this reaches 5, the 0 will clear all of them. Another choice would be to replace the AND, which is the 74LS21, and the inverter with a NAND, which would be a 74LS20. And I'll put it here so that you can see it. That 20 is the 4-input NAND. So you can use the NAND if you'd like instead of the AND with the inverter. I'm going to leave it like this though so it's more clear. So now if I press play at the moment, you're going to see that it's going to count. Like, it starts at a weird place, but once it reaches 5, it's going to tell all the flip-flops to clear. So it's 4. Now it's going to tell it to, whoa, it should have told it to clear, and it did. Now, take a moment and think about it. Why is it that it does not show a 5? It glitches. It kind of just shows it for a fraction of a second. There. So you have to remember that the clears of all these flip-flops are not synchronous with the clock. They immediately get a signal and they override. So let me see. This green wire, the moment the AND gate gives it a 1, inverted to a 0 so that it clears, immediately it clears. So yes, it's showing a 5, and then within a fraction of a second it says, don't show a 5, show a 0, 0, 0, and 0. So if I really want to count up to 5, what number do I have to put here so it doesn't override the 5? If you answered 6, you're correct. So I need a 4 and a 2, so I'm going to put the inverter on the 1. So at this moment, I have a 4 and a 2, and that's a 6. So if I press play in my simulation, I should have a counter that counts up to 5, shows the 5, as you're going to see. So it shows the 5, and the 6 is the one that it's overwritten. So it doesn't show the 6. Now, I know you're thinking, well, that's not very good. However, this is a very simple type of counter, so we overlook that glitch and we use counters such as this one for very simple counting operations. So now that little probe was just a stepping stone. I'm going to delete it now. So here we have a counter that is counting from 0. I'm going to put it here, a counter that is counting from 0 to 5. Okay? So, oh, by the way, I'm going to optimize this or clarify. This is a up counter, flip-flop up counter from 0 to 5. 0 to 5. Just so that you're sure. Okay, now I put the text together there. Okay, so this counter is counting from 0 to 5. Now, so the note that I would like to make is this. The ending limit of a counter. What I would like to say on this one is that the ending limit, you have to and at one number past the ending limit. This is due to it's because the clears don't wait for the clock due to overrides being asynchronous. Okay, so they don't wait for the clock, and so you have to realize that it's going to do it immediately. So there you go. So the ending limit of a counter, and at one number past the ending limit. This is due to overrides being asynchronous. You always see the glitch if you put an oscilloscope, and in simulation you may see that little glitch here. However, if you were building this or you program a chip, a microcontroller, or an FPGA or any chip, or just connect it to LEDs on a breadboard using the 74LS76s, the JK flip-flops, you will not see it. Your eyes are not that, the refresh rate of our eyes are not that fast. Okay, so let's move on to changing the lower limit. Actually, let's do a quick test before we move on. Let's say I wanted to count up to 12. Okay, what modifications do I have to put here at my ending limit so that instead of ending at the number that it was now, it ends at 12? So here we have a 4 and a 2, which is going to be stopping at 5. But now we modify it to 12. So what do I modify it to? Take a moment to think about it. What number would I have to put here so that it ends at 12? If your answer was 13, you're correct. And so let's move that to 13. 13 would be an 8 and a 4, that's 12, and a 1. So I have to put the inverter on the 2. I'm sorry, yeah, on the 2 and nowhere else. So here it'll stop when it's an 8 is okay, a 4 is okay, that's 12, and a 1 is 13. So let's see. This should count up to 13. If you want to make it count a little bit faster, you just double click on our clock source, whether you're using this digital clock or a 555 timer or the clock source under power sources for multisim. It'll work out all right. So here we got A, B, that's 12, that's 13. I mean, that was 12, sorry, and then it reset back to 0. So 8 and a 4 was 12. Here we go, 5, 6, 7, it's a little bit slow, 9, 10, 11, shows the 12, and the 13 gets overridden. Cool. All right, so now, what happens if I don't want to start back at 0? Okay, what if I want to start, I don't know, let's start with something small like 2. So how would I modify my clock so that instead of forcing all my flip-flops to clear, meaning 0, 0, 0, 0, I don't force a clear, I force maybe some to clear but others not, so that I have a 2 in binary. I like to highlight the fact that this is my ones place flip, what did I do? Oh, it rotated it. This is my 2's place flip-flop, this one is my 4's place flip-flop, and this one is my 8's place flip-flop. Okay, don't get them backwards. Sometimes you think that this is the ones because it's on the right, but remember the fastest blinking one is the least significant bit, which is the ones place. So now, what I want to do is whenever the AND gate reaches its ending limit, I don't want to just turn on the 0, 0, 0 for clear for all of them. What I want to do is I want to force the 8 to clear, the 4 to clear, and the 1 to clear. But the 2, I don't want to clear it. I want to force it to be a 1 on. Now, remember the function of the flip-flop? You don't clear it anymore. Okay? What you do is you would preset it. So by doing this, what I am accomplishing is that whenever the AND gate gets a 1 here, it says, nah, don't show a 13. Override the 13, make the 8 a clear, so 0. Make the 4 a clear, 0. Make the 2 a preset, which is a 1 at the output. And make the 1's place a clear. So check it out. I'm going to speed this up a little bit because it's a little bit slow. Here we go. So now if we're going to count, it's going to count all the way to 12, and then the 13 is going to get overwritten. 9, 10, 11, 12, override with a 2. Do you see that? So again, 8, 9, 10, 11, 12, override with a 2. Now think about it for a moment. Let's change this one. So in order to change the restarting limit, here I'll make a note here. Restarting limit of a counter. The notes that I want to make is connect to top preset to force flip-flop to a 1, and connect to bottom clear to force flip-flop to 0. Okay, so here I'm talking about the green wire. So let's see if you understood that. Here we have it forcing a 0, 0, 1, 0. Clear, clear, preset, clear. Let's modify it so that it starts at 5 instead. What modifications do I have to make to this green wire so my starting limit changes to a 5? If your answer was force the 8s and the 2s to clear and the 4 and the 1 to preset, you're correct. I'm going to delete all those connections and start from scratch so that I don't mess it up. So a 5 would be a 4 preset to a 1 and the 1 preset to a 1. OCD, I don't like this. There it is. Okay, so now I force the 4 and the 1 to a 1. And you may think, oh, I'm done, I force it to 1, but you don't know the state of the 2 and the 8 flip-flop. Well, you probably can guess it, but you don't always know it. So what we're going to do is we're going to make sure those turn off by connecting those to clear. So now when it reaches 13, it's going to get overwritten. It's going to show a little glitch at 13, but we'll pretend that we don't see it for this application. And then it says, don't show 13, show a 0, 1, 0, 1. Now, you can see that I disconnected these. I cannot leave them just hanging. It's not good practice to leave things hanging. So I'm going to copy and paste. And I know it's kind of weird that I'm rotating VCCs because, I don't know, it's kind of like seeing the ground upside down, but it makes it a lot cleaner, for me at least, to not have wires everywhere. So if we do this properly, we have a counter that counts up to 12 and then starts back at 5. 10, 11, 12, 5, 6, 7, 8, 9, 10, 11, 12, 5, 6, 7. There you go. So there you have it. You have a counter that counts forward, has the ending limit at 12 in this case, and the starting limit at 5. Now, a quick definition so that you know it. The definition is modulus. Some people call it mod. So that is basically the number of states in the counting sequence. So for example, this one that we have is counting from 5 to 12, 5 to 12. So let's see, how many is that? Modulus, this is equal to, let's see, count out loud. It counts 5, state 5, 6, 7, 8, 9, 10, 11, 12. So that is 8 states, modulus 8 counter. Let me check. I don't know. I think I may have counted wrong. Okay, again, use your fingers. 5, 6, 7, 8, 9, 10, 11, 12. Yeah, 8. I used 2 hands. Okay, so this is a modulus 8 counter. If you were counting, let's say 1, 2, 3, that would be a modulus 3 counter. You could also have another type of modulus 3 counter where you count 0, 1, 2. It has 3 states. All right, so now if you understood this, I have a question for you. The question is, let's say I modified this to count in reverse, a down counter. Here, I'll do it. I'll highlight all of this, Control C, get a new paper so that I don't modify this one. And I'm going to paste it. So all this, I just pasted my entire work again on a new page. Here we go. I want to modify this counter to count down, from 12 down to 5. Okay, so what modifications do I have to make? First of all, let's make it count down. So the modification that I have to make to count down is to change the falling edge to a rising edge. So I changed the clock. Notice I didn't change the connection of the output. The output's always Q. What I'm going to do is I'm going to connect to the rising edge, so to the not Q. And yes, I know there's a glitch. Multisim doesn't show the inverter on the output of the inverted Q, but functionally it's fine. Now, the question is this. See if you're paying attention, if you understood this. If my ending limit is now 5, what is one number past 5 when you're counting down? What is one number past 5 when you're counting down? If your answer is 4, you're correct. So, because if we're counting down, it would be like, for example, 7, 6, 5, and then the 4 would be the one overwritten. If you said 6, it would count only down up to 7. So we want to stop it at 4. That means that I have to put an inverter on the ones that I don't want to be on. So that would be a 4. The 4 would be overwritten. I want to start back at my new starting limit, which is 12. Okay, so notice that the counting forward and in reverse, the starting limit and the ending limit swapped locations. So now the starting limit is 12. Now I'm not going to force, this one was forcing a 5. So how do I force a 12? To make a 12, I need an 8 and a 4. Correct? So then I need to force the 8s to be on. I need to force the 4s to be on by activating the presets. I need, oh, I don't like that. I need the 2 to be off. So I clear it, and the 1 to be off. And then again, the unused overrides, the preset and clears that I don't use, I just disable. If I did this correctly, let's see, hopefully I didn't make a mistake. I can see that it's just countdown. Now, when you first start the counting sequence, you saw it started at 3. It's somewhere outside the sequence that I designated. But that's all right. After the first pass, it should normalize. And it does. You can see here that it goes down 8, 7, 6, 5, 12, 11, 10, 9, 8, 7, 6, 5, 12. Okay? So that's it. You have your counters. You can make it count forward. When you're counting forward, let me stop the simulation. When you're counting forward, this is my up counter. The ending limit is the highest number, and you have to go to a higher number. So we stop it at 13. Now, you don't go one past on the restarting limit. The restarting limit is exactly the number that you designate. Okay? And to count in reverse, to count down, the ending limit is now the smaller number, and the ending limit is 1 less than that. So in this case, it would be 4. And the restarting limit is exactly the number, and we're starting at this case 12. So there you have it. Forward counters, reverse counting, and by the way, the name, the correct name for these counters are truncated. Truncated. I can't spell truncated, meaning that we don't let the entire sequence happen. We truncate it. Like if you cut a tree, I guess it stops growing here. It would be the same idea. Truncated means you don't allow it to go through its entire counting sequence. You stop it and start it at different limits. There you go. Thank you for watching.